Okay, so this session talks about multi-agent systems basically. In other words, if you are trying to solve a problem by using more than one agent, so you need to see how you coordinate all the agents together. So mainly it talks about some applications of multi-agent systems and a little bit on how you can see how well your multi-agent system is doing by doing some evaluation. So a multi-agent system is one where you have a lot of agents which interact with each other. Okay, so they can either interact in a cooperative manner or they can interact in a negotiative manner. Okay, or they may be confrontational with each other. All these things are possible. Okay, it depends on the problem, what are the goals, etc. So you need to basically cooperate, coordinate, and negotiate basically. Okay, so these are the three things which need to be done. Okay, so you have coordination between the agents, either it is cooperation or competition, right? So under competition you have the negotiating agents where the negotiation is done or you can offer bids, etc., right? And cooperation is when you combine together to solve a problem. So you want to carry out something, okay, so either it's centralized or distributed, whatever, right? So this is coordination is the mechanism for ensuring that agent activities have some relationship between them. Cooperation is when you have some degree of communication between the agents, right? So that if you're solving some task together, then you find that you can complete the task quicker, okay? And you can also share some of the resources, or if one agent carries out a task, it can give, or it has some information, it can give that information to the other agent basically, okay? So these are some advantages of having some type of cooperation among agents. Negotiation is you have some type of agreement between the agents on some common viewpoints or plans which you are doing. Okay, what is the negotiation process? The agent will contact the other agent to offer or request resources or service, right? Other agents identify what can be supplied under what condition. Initiating agents accept the conditions, and the supplying agent can commit to provide that resource basically. So we have a number of applications of these type of things. So let me give some examples of multi-agent systems. Okay, so this multi-agent system is actually for getting jobs done, okay, based on what is called the e-marketplace. Okay, so you have something like this. So you have the e-procurement server which actually procures jobs. So the users can interact with the e-procurement server and ask for jobs which it wants to be carried out, right? And that is actually fed into the e-marketplace server. And the e-marketplace server is in touch with a number of agents, okay, and it will put out that this job is there to be done. And that job, you have all these agents which can see what are the jobs which are available and they can bid for a particular job. So the e-marketplace server will see what are all the jobs that have been, who are all the agents who have bid for a job, and they will choose one of the agents and then communicate with that agent to carry out the task. And when the agent carries out the task, the agent will again communicate with the e-marketplace server, and the e-marketplace server will put out that the job is completed in the e-procurement server. And the users who have asked for a particular job can always check in the e-procurement server what is happening to their job, basically. So that is the entire thing. So you can see an example of that architectural design here. Okay, so this uses the J2EE server, and you have all these, and you have the client web browser. So the users actually communicate with the server in this way, and then you have the database at the other end. So we can see the entire process here. You have the customer who will give in the job, then the administrator will trigger the bidding process. Okay, and then you have agents who can either register or unregister from the system. So whenever they don't want, they can unregister from the system. So this is the system which is used. It's a fully integrated web-based application which consists of e-procurement and e-marketplace server, right? So this is the entire sequence or the workflow that happens, right? So you have customer submits a job request, agent owner registers its agent with the e-marketplace, and agent owner will specify what are the resources it has, and the administrator connects to the e-procurement to download the jobs, and then it's broadcast to all the registered agents, and all the agents perform their own planning and scheduling, okay, and they make bids for the job if they want to. And the bids are returned to the e-marketplace where the supervisor agent will do a final allocation and inform the agents about the allocation. And all agents update their original plans, and customer can check for status of its job from the e-procurement server. Administrator can view all transactions from the e-marketplace server. And each agent owner can view its agent's plans. Okay. And the agent owner can decide whether to go to the next round of bidding or not, or unregister, basically. So this is one system we can see over here. Okay. Then we can talk about the negotiating agents, which are in this way. You have two types of agent. Each of these is an agent, and you can see all the blue ones are the functional agents and I are the information agents. So it's only the functional agents which take place in the negotiation, and the information agents only give information to the functional agents over here. Okay. And you have what is known as the agent communication language. So the agent communication language actually has all these what are called the performatives. Okay, so only these are the performatives which are used for communication between one agent and another agent. So you have things like accept proposal, acknowledge, call for proposal, call for modified proposal, reject proposal, proposal, terminate, withdraw, etc. So this gives you the list of performatives that are basically available. Okay, and in the negotiation systems, you can have different configurations or architecture of your computer system. Okay, so these are the negotiators, the yellow ones, and these blue ones are the negotiating support system, right? So the negotiate support system gives support to the negotiator. So you can have just one negotiating support system, okay, or in different configurations, you can have different NSS for each of these negotiators. And then you have what is called the domain auxiliary system. So the auxiliary, in this case, you just have one domain system. So whereas here, you can have the auxiliary system, and you could have also a domain system. Whereas here, each one has their auxiliary system, and you have one single domain system. So these are different configurations that can be used. Okay, so in configuration 1, there is one negotiating support system. Okay, and this negotiating support system is maintained by a third party, basically. Okay, and in configuration 2, each party is supported by one negotiating support system, which is under that party's control. Okay, so there's no third party involved, basically. And configuration 3 involves several negotiating support systems. Okay, and each one has their own auxiliary system. So and you can also have other such configurations. So here, this is showing how negotiation agents are used for buying and selling on the web, right? So you have a buyer here, and the buyer has a negotiating agent of its own, right? So this is the negotiator, and that is the auxiliary system, and it's in touch with negotiating agents, okay, on the web. And these negotiate it will tell its requirements to the negotiating agents, and the negotiating agents will travel in the web. Okay, so they are mobile agents which go in the web, and like they go to other locations and find out the information about sellers, right? So the sellers will communicate via the negotiating support systems, or it could be a negotiating agent directly. You may be getting information, right, from the sellers. So this is one way, one application, okay, how negotiation agents are used. So the NSS plays the role of the front end and interacts with the user and provides specification for the agent, and that interacts with other agents, and the buyer interacts with an agent which represents his interest. It then invokes agents that roam the web in search for potential sellers, and these agents will carry offers and counter offers, right, for whatever the sellers are selling, between the localized agents and the NSS. Okay, so that is one thing. Another one is this entire thing is a negotiating agent. Okay, so let us see the parts of this negotiating agent. So you have a number of software agents. Okay, and the agents participate in the negotiation. They communicate through a broker. So basically, a negotiating agent consists of a communication module. So here we have a communication module, a control module, a knowledge base, and a reasoning module, right? And the control module is like a state chart, okay, and it controls the entire agent. So what happens? It contains a memory which contains a history of past decisions and interactions. So that's the knowledge base. A communication model responsible for receiving and sending messages to other agents. A reasoning module which encodes the decision making part. Okay, so it's the one which decides whether to bid or not, what is the bid to be given, etc. And a control module which coordinates the other components of the agent. And the reasoning model uses what is called the defeasible logic. Okay, we'll see what the defeasible logic is. Okay, so this gives you the overall bidding process. Okay, this is an extract of the control module, which participating in various auctions. Okay, and deciding whether to bid or not, whether to accept or not, etc. Okay, now let us look at the defeasible logic. What is this defeasible logic? Again, defeasible logic is a type of non-monotonic logic. That is logic which can change over time, right? So it takes, if we take monotonic logic, it means that any statement which is made or anything which is true, say a proposition P which is true at point T, will be also be true at point T plus 1 or will be true at point T plus 2. But in non-monotonic logic, that is not the case. So let us look at this defeasible logic. Okay, the facts are denoted. Okay, for example, emu tweety. That's just like in the predicate logic, right? And then you have rules of two types. You have strict rules and defeasible rules. The strict rules will be like this way: a1 to an, that is the left hand side, implies b, and a1 to an implies b. This is what is called the first one is called the strict rules. So the strict rules are applicable at all times. And then you have the defeasible rules. Defeasible rules are rules which can be defeated sometimes. In other words, it may not be always true. Okay. So an example of a strict rule is emu x implies bird x. Okay, which means every emu is a bird. Okay. Defeasible rules are like this: bird x implies fly x. So you are saying that birds usually they are able to fly. Okay, but if you have some other evidence which says that the bird cannot fly, then unless you don't have any other evidence, then you can say birds fly, basically. Okay. So then you have defeaters which are there to defeat the defeatable rules. Okay, for example, if we have something like heavy x implies fly x, not fly x, right? Which means that if the bird is heavy, then it is not able to fly, right? So if you have a defeatable rule, you can say that it's true only if there isn't anything which gives evidence to say that it is false. Okay. You also have rules where you can use the superiority relationship. Okay. So you can have a rule which says bird x implies fly x, and you can have another rule which says emu x implies not fly x, right? Now when you are using this logic, do you use the first one or do you use the second one? Okay, if you are using, suppose you are talking about an emu, right? You know that emu is a bird. You have already come up with emu is a bird. So when emu is a bird, it should be able to fly according to R. But according to R dash, it's not able to fly. So which rule do you use? So you have what is called the superiority relation. So you're saying R dash is superior to R. Okay, so you're using this symbol which says R dash is superior to R. So when you have something like this, then you know that R dash is true for emu, even though it is a bird. Okay. You also have what is called the P complementary literals. So if you take one proposition P, this CP will contain all the literals which are complementary to that. Okay, so for example, you can have something like C married A. Okay. So what are all the propositions which are complementary to married A? So married A is, one is not married A, another one is bachelor A, etc. Right? So these will tell you that married A and bachelor A cannot be true together, right? So that will help you in using this type of a logic to come up with conclusions. So now suppose we have a conclusion. A conclusion P can be derived if there is a rule whose conclusion is P, right? Whose prerequisites are either already proved or given in the case at hand. Okay, in other words, it's a fact. And any stronger rule whose conclusion is not P has prerequisites that fail to be derived. Okay, so all these things will have to be checked before you say that conclusion P is right. In other words, conclusion P is derivable when P is a fact or there is an applicable strict or defeasible rule for P, and either all the rules for not P are discarded or every rule for not P is weaker than an applicable strict or defeasible rule for P. So this is what is called the defeasible logic. Here we talk about using a Bayesian network for negotiation, right? So A quotes a price for its car and negotiation continues till B accepts A's offer. We assume B has a genuine desire to buy a car very similar to A's, and that price is the primary issue. So A offers a price depending on its a priori belief of B's capacity of payment and its evaluation of A's car. A may call in a third agent C, and based on the belief of its rapport with C and C's evaluation of its car, A may ask C to recommend its car to B, right? So you can actually put this whole set of values we have into a belief network in this way, right? So when you have a belief network, a Bayesian belief network, right, you could call it a decision network because you have a decision node here, and that decision node will help A to make a decision, right, on what to basically do. So any problem which is there can be converted into a Bayesian belief network in this way, and then a decision can be made to see what needs to be done. Okay. So here we come to when you have multiple agents doing a task, okay, how do you go about doing this task, okay? So we have a set of actions AI for every agent A, right? So that agent I can do any of these actions AI, okay? And this gives you the number of actions that you have, okay? And then you have a set of states S, okay, which is belongs to the distribution DS, okay? And then each agent I has a policy which is called Pi of S, right, at time t, which maps from a state S to a particular action, okay, or a set of actions. So when I learn that at time t that it is in state S, it will take action pi I t S, okay, that's the thing. And then you have the overall policy, okay, which is this one, okay. Agent's I learning algorithm will try to reduce the discrepancy between its policy and the overall policy, okay, by using the payoff it receives. The probability that an agent will take a wrong action is given as probability that this pi I t of S is not equal to pi I t of S. That's the overall policy, right? And you have things like what is called the change rate. What is the change rate? Change rate is the probability that an agent will change at least one of its incorrect mappings in delta TW for delta T plus 1 W, okay. And so it captures the rate at which the agent's learning algorithm tries to change its erroneous mapping. Okay. So if it has an erroneous mapping, the probability that it will change it to the correct mapping. Okay. Then you have the learning rate. Okay. The learning rate is the probability that the agent changes an incorrect mapping to a correct one. Okay. That is the probability that delta t plus 1 w is equal to delta t w, which is the overall correct uh, learning, right? Then you have the retention rate R, which is the probability that the agent will retain its correct mapping. So delta t plus 1 w equals delta t w, given that delta t w is equal to delta t w, which is the correct mapping, right? Then you have what is called the volatility, which is the probability that the target function changes from time to t to t plus 1. So volatility means that there is always a change, right? That is the probability that delta t. So this is, we are taking for the overall system, right? Delta t w not equal to delta t plus 1 w. Okay. So volatility. It is the speed of the target function in the moving target function problem, with the learning and retention rates representing the speed of the decision functions. So you can have what is called the impact measure. So Ij represents the impact that I's learning has on J's target function. Okay. And it's the probability that delta J Wt will change given that delta I is not equal to. So if your delta is not equal to this, then the probability that this will change, right? That is called so let us go into what is called the collective intelligence. Okay, so collective intelligence is the, again, when you have multi agents and you are trying to collectively learn something. Okay, so you have a global utility function U, capital U, S and A. Okay, that's the state and the action, which tells us the value for each vector. So this gives you all the actions possible, A1, A2 to AN. So for any particular A, okay, what is this utility function for each vector of actions? Okay, so our problem is then to define the agent's reward function UISA. Okay, that is the small ui for the utility function for a particular agent I. Okay. So if you put UISA is equal to capital US of A, that's the overall utility. Put it as equal to the overall utility. It can lead to agents receiving an uninformative reward. Okay. So that is not going to solve the problem. Okay. So here we can quantify the preference of agent I with a particular action A, right? So this will be equal to, you take all the possible actions, right? And you find the difference between the utility of using this action and all the other actions, right? And if this is not equal to 0, this is put as equal to 1. So that's the Heaviside function which is used here, right? So this will give you actually a fraction between 0 and 1. Okay. You can also find the global preference function where you take the global preference and use every action A. Okay, that is you are not choosing a particular agent UI like over here, but you are taking the overall utility. Okay, and again you can get a value for this between 0 and 1, okay, for this preference function. And so if the agent's preference is similar to the system's preference, okay, then the agent's learning mechanism will try to converge towards the desired system's preference. So if you find that for a particular system, for all agents I, if the preference is equal to the overall preference, then it is called a factored system. This means that they provide the correct incentives to the agents in all situations basically. So factored systems are more likely to converge to the set of policies which maximize the overall U basically. And we can also talk about what the impact, that a particular agent's action has on the other agents. Okay, so we specify what is called opacity over here. So the opacity of a particular agent I, okay, for a particular action A, will be actually here what you're getting is that the utility of using the particular action A, okay, and what you are doing here is you are removing this action A and you are introducing the action A dash, right? And here what you are doing is you are removing the you are doing the opposite basically, okay, introducing action A dash, removing action I, whereas here you are removing action A dash and keeping action I. So if you are going to do this and say what is the opacity value that you are going to get. So if the opacity is 0, it means that the agent's rewards are the same regardless of the actions taken by the others, right? So the other agent's actions has no impact on what this agent does. And if the opacity gets larger, it means that as the other agent's actions change, the reward the agent will get, it will change the reward that this agent will get, right? So what you find is that if the opacity is 0 for all the states and action vectors, then the multi-agent learning problem is reduced to a single agent learning problem because they are all the same, right? There is no difference. So agents have no effect on each other's target functions, right? So as it increases, you find that that effect actually keeps increasing. Okay, so that's the basic way in which, so you can see that using all these all these factors which I was talking about and all these equations, you can actually rate the in a multi-agent system how your multi-agent system is really doing. Okay, is it performing at its optimal or is it not? Okay, so that's the basic idea of these equations which were given over here. So with this I'll stop this session.